Let us take one more example. Find the principal solutions of sin x is equal to half. We know that sin pi by 6 is equal to half. Also, the sine function is positive in the second quadrant. So when x is equal to pi minus pi by 6 or 5 pi by 6, the value of sin x is equal to half. Hence, pi by 6 and 5 pi by 6 are the principal solutions of sin x is equal to half. We know that trigonometric functions are periodic functions. The functions sine, cos, cosecant and secant repeat after an interval of 2 pi, while the functions tan and cot repeat after an interval of pi. This implies that we can generalize the solutions of trigonometric equations with the help of the periodicity of trigonometric functions. For example, sin theta is equal to 0 implies that theta is equal to n pi, which gives all the solutions of the trigonometric function sin theta is equal to 0. When the solution set of a trigonometric equation is an expression involving an integer n, such a type of solution is called the general solution of the trigonometric equation. In this case, theta is equal to n pi is the general solution of the trigonometric function sin theta is equal to 0. Similarly, cos theta equal to 0 implies that theta is equal to 2n plus 1 pi by 2, which gives all the solutions of the trigonometric function cos theta is equal to 0. In this case, theta is equal to 2n plus 1 pi by 2 is the general solution of the trigonometric function cos theta is equal to 0. Let's now prove some theorems that will help to find the general solutions of trigonometric equations. The first theorem is, for any real numbers x and y, sin x is equal to sin y implies that x is equal to n pi plus minus 1 whole raised to the power n into y, where n belongs to the set of integers. Let's begin with the proof. For any real numbers x and y, we have sin x is equal to sin y. This implies sin x minus sin y is equal to 0. Now, sin x minus sin y is equal to 2 cos of x plus y by 2 into sin of x minus y by 2. That is, the product of cos of x plus y by 2 and sin of x minus y by 2 is 0. This implies either cos of x plus y by 2 is equal to 0 or sin of x minus y by 2 is equal to 0. We know that if sin theta is equal to 0, then theta is equal to n pi, and if cos theta is equal to 0, then theta is equal to 2n plus 1 pi by 2, where n is any integer. Therefore, x plus y by 2 is equal to 2n plus 1 pi by 2, or x minus y by 2 is equal to n pi, where n is any integer. Or x is equal to 2n plus 1 into pi minus y, or x is equal to 2n pi plus y, where n is any integer. We know that minus 1 raised to the power of 2n plus 1 is equal to minus 1, and minus 1 raised to the power of 2n is equal to 1. Therefore, x can be written as 2n plus 1 into pi plus minus 1 whole raised to the power of 2n plus 1 into y, or x is equal to 2n pi plus minus 1 whole raised to the power of 2n into y, where n belongs to the set of integers. Now, 2n plus 1 constitutes all the odd numbers, and 2n all the even numbers, and all the odd numbers and even numbers taken together make the set of integers. Hence, on combining the two results, we get x is equal to n pi plus minus 1 whole raised to the power of n into y, hence the result. Let's now move on to the next theorem. For any real numbers x and y, cos x equal to cos y implies that x is equal to 2n pi plus or minus y, where n belongs to the set of integers. Let's begin with the proof. For any real numbers x and y, we have cos x is equal to cos y. This implies cos x minus cos y is equal to 0. Cos x minus cos y is equal to minus 2 sine of x plus y by 2 into sine of x minus y by 2 is equal to 0. That is, the product of sine of x plus y by 2 and sine of x minus y by 2 is 0. This implies either sine of x plus y by 2 is equal to 0 or sine of x minus y by 2 is 0. We know that if sine theta is equal to 0, then theta is equal to n pi, where n is any integer. Therefore, x plus y by 2 or x minus y by 2 is equal to n pi, where n is any integer. Or x is equal to 2n pi minus y, or x is equal to 2n pi plus y, where n is any integer. On combining, we get x is equal to 2n pi plus or minus y, where n is any integer, hence the result. Let's prove the last theorem. If x and y are not odd multiples of pi by 2, then tan x is equal to tan y implies x is equal to n pi plus y, where n belongs to the set of integers. Let's begin with the proof. Suppose x and y are not odd multiples of pi by 2 and tan x is equal to tan y. This implies tan x minus tan y is equal to 0. Or sin x upon cos x minus sin y upon cos y is equal to 0. Or sin x into cos y minus cos x into sin y upon cos x into cos y is equal to 0. Now, sin x into cos y minus cos x into sin y is equal to sin of x minus y. So we have sin of x minus y upon cos x into cos y is equal to 0. This implies sin of x minus y is equal to 0. We know that if sin theta is equal to 0, then theta is equal to n pi, where n is any integer. Thus we can say that if sin of x minus y is equal to 0, then x minus y is equal to n pi. Or x is equal to n pi plus y, where n is any integer. Hence the result. Let's now find the solution set of sin x equal to minus 1 upon root 2. Let's begin with the solution. Given sin x is equal to minus 1 upon root 2. Now, sin pi by 4 is 1 upon root 2. Therefore, sin x is equal to minus sin pi by 4. This further implies that sin x is equal to sine of minus pi by 4, since sine of minus theta is equal to minus sine theta. This implies x is equal to minus pi by 4. Let alpha be the principal solution of sin x is equal to minus 1 upon root 2. Then alpha is equal to x is equal to minus pi by 4. Recall that for any real numbers x and y, sin x is equal to sin y implies x is equal to n pi plus minus 1 whole raised to the power n into y, where n belongs to the set of integers. The solution set is equal to n pi plus minus 1 whole raised to the power of n into minus pi by 4, where n is any integer, or n pi plus minus 1 whole raised to the power of n plus 1 into pi by 4, where n is any integer.